Okay, alright, we now have physics video. On the density of a steel pipe, we're going to look at the data analysis using Excel. Alright, so let's get right into it. So some important things we need to first consider. Here we have a blank set of data, raw values just plugged in straight from an experiment. We've got mean quantities, we've got our limit of setting evaluated using standard deviation. Divide this quantity, that gives you your error of the mean. What else we got? Certainty in error, total uncertainty error in length. So we've got all the data here. Now our job is to try and organize this and to present it in a meaningful way, showing correct significant figures, ensuring all calculations are correct, and making it presentable so we can then refer to it and draw on it. Okay, what we can do first is let's give it some structure with some borders, and just this helps to make sense of the quantities. And generally, when you've got a set of columns, we want to highlight all the columns of pertaining to the same type of quantity. So in this set of data here, you've got 6, 7, 8, 9 columns, all pertaining to measurements of length. You've got repeated lengths, you've got the mean length, and you've got the error associated with it. Okay, so we're going to put it all, or put a big border all around it. Same with thickness, same with diameter, and then the volume of the pipe and the percentage error in volume. Some of these rules need to be reviewed to make sure that they're correct. Alright. Then we've got some spacing. Some of the headings we can't see properly, so we've got to fix up some of the spacing. So what we can do, a quick easy way of doing it, you highlight all the headings and then you hit wrap text, and that brings them all down together so we can see them, and just space them out a little bit like this. Okay. Alright. So from here, just bring that down. We'll refer to these rules in a second. Alright. Now another thing that's important to do with data, particularly when we've got lots of sets of numbers of different degrees of accuracy, is to consider what are the most significant amount of figures we really should be showing in our number. So to make that decision, you need to consider the measurement that is of the highest degree of accuracy. And then you also have to consider the measurement that is of the lowest degree of accuracy. And what I mean by that is using our measuring device, which quantity has the least amount of significant of decimal places. That is as accurate as we're able to measure that quantity. And so data is consistent, we need to ensure every other data point has the same amount of decimal places. So let's refer to length, because the length was measured, most of the lengths were measured with a caliper, and the caliper allowed us to measure it accurate to about 4 decimal places, and that was as accurate as we're able to measure. Some of them here to 2 decimal places are measured as precisely as we can to be 0.05, and as a whole amount. We didn't measure any more lower than that. So 4 decimal places is what we're going to decide on as our significant figures. So highlight all your data set like that, and now select here to decrease the decimal. So we've got 4 decimal places, 4 decimal places. Good. Now every data point is as accurate to 4 decimal places. Good. And we can see this one here, volume of a pipe. To 4 decimal places, nothing's there. Volume was the type of quantity that was even smaller amount than 4 decimal places because of this meters cubed business. So we really need to consider different formatting for this number. The best type is scientific notation, because that gives you this notation here, gives you factors of 10 or powers of 10. Okay, so now we can represent that number to 4 decimal places. There we go. It's accurate to 4 decimal places, every number is, and it has the times 10 to the power of negative 6 factor to help adjust the numbers there. Excellent. So we're getting there. Now, what's next thing to consider is let's have a look at some of the results in our calculations. If we consider the standard error, here we've got 6 data points for the first specimen for length, and the standard error, which is the measure of uncertainty of due to the randomness in measuring the length. We've got the standard deviation, which is correct, times 1 on the square root of 6. That's the correct rule. And because we've got 6 data points, we've got the square root of 6 value there. Let's go to the next one. And 0.0013 is a bit of an order of magnitude different to 0.0003. It's like a factor of 10 different there. And it's because it's important to ensure that we have all the correct values used in our formula. So for 5 measurements of length, we need to have a 5 in the square root here. Same for all of them. Alright. Good. So that the rule for standard error seems consistently correct. Let's now come over here. Total uncertainty is this limit of setting combined with the limit of reading. This limit of reading is due to the limits in our measuring device. So what measuring devices did we use to give us these limit of readings? And it's important to note that down. So we're going to insert a column. Oop, not that way. Let's insert a column here. Ah, bugger. Try again. Insert. There we go. And here we'll describe as the measuring device. Now, what measuring device did we use for that gave us this limit of reading? It's quite of a small amount. That one was the caliper. And all the 0.0001 limit of reading errors associated with using the caliper. And this one here, 0.5 mil, was using the ruler to measure the length. Okay, so this was the only time we swapped from a caliper. Okay, there it is. This is the only time we used swapping from a caliper to the ruler. So when we were measuring the length. And as you can see, these lengths are about 15 centimeters. Well, that's much too long for the caliper. These ones are about 11 centimeters. That's still within the range of using the caliper, so that's why we chose it there. Alright. Now, let's check our volume formula. We have the first quantity, pi times L. L is the mean length. Okay, I3. And then multiplied by the thickness, L3, which is the green one. There it is, thickness. and then multiply by the bracket. The diameter, purple, subtract the thickness. So that's correct. Alright, let's come over to percentage error in volume. Now, let's have a look at some of these values. It's about 13%, 10%, 10%, 52%. That seems a bit out of scale. So that rings alarm bells. Let's check that formula. So here it is, our uncertainty in volume. We've got rational terms here. So this says the error in L on L. That's the first one. Let's check. The error in L was the error in measuring the length was done with the ruler in this case. So that's the limit of error for the ruler. So that's right. Now the next term looks at thickness. The thickness of the pipe. So the thickness of the pipe was actually a very small measure. It's only such a fraction. We actually use the caliper to measure the thickness. So we can't go ahead and use the limit of reading for a ruler for that error quantity here. That's one. We need to use the limit of reading for a caliper. This number. Same goes for the error in the diameter and the error in thickness for this term here. And by making that adjustment, that correction, you can see now it's gone 50% down to 11%. So that's in the right order of magnitude. The only other error is this one here. So it has the same issue, choosing the ruler for limit of reading instead of a caliper for thickness and diameter. So thickness uses a ruler, uses the caliper there, and this quantity for error in diameter uses the error for caliper, and this one here for the error in thickness uses the caliper. And there you go, you can see it's going 50 down to 10%. Alright, excellent. So we're almost there. We've got our volume and our error in volume, and we have our mass. But we don't have our error in mass. And the error in mass is also an important quantity because mass was measured with the electronic balance, and even that has its limitations in how accurate we can measure quantities. So the limit of reading in mass is important to consider. Let's have a look. We were measuring mass to 1, 2, 3, 4, 5 decimal places. So let's have half of that quantity, 0.00005. Okay, and by putting that in, because we've set it at 4 significant figures, Excel is going to round up to the nearest 10, the next one over here. So rounding, that's acceptable to ensure we're all on 4 significant figures, and still that amount is such a small fraction of the total amount of mass we've measured. So if I just want to check to see how big of a fraction, what proportion does it make for one of a measure of mass, it's quite negligible. It's very small. It's 0.02%. So it's a small contribution of error, but it's still worth estimating. Okay. So the data is sorted at this point in time, and from here, what the next thing we might be interested in is a graphical representation of our mass of the pipe and the volume of the pipe and its associated error. And then we can, from then, using density is equivalent to mass divide volume, we can get the gradient of the graph and to work out the density. So that will be for our next video.